Imagine holding a kidney in your hand. Feel its weight, its texture. It looks and feels real, almost indistinguishable from the real thing. But this organ was never inside a human body. It was printed layer by layer by a machine, a symphony of technology and biology working in perfect harmony. This isn't science fiction conjured up in a Hollywood studio. It's happening in labs right now, August 5th, 2025. Scientists and engineers are collaborating, pushing the boundaries of what's possible. The first successful 3D printed organ transplant in a human might not be the heart, the symbol of life, or the liver, the body's detoxifier. It could be an ovary, a testament to the power of this technology to address a wide range of medical needs. Scientists have already printed functional ovaries in mice which, remarkably, gave birth to healthy pups. This is a crucial step, proving the viability of bioprinted organs. This quiet success signals a monumental shift, a paradigm shift in how we approach organ replacement and regenerative medicine. A future where organs are created on demand, precisely tailored to the patient's needs, not harvested from deceased donors, eliminating the agonizing wait and the risk of rejection. The science behind this is profound, a complex interplay of various disciplines, blending biology and engineering in ways never seen before, pushing the boundaries of human knowledge and capability. For decades, the organ transplant list has been a symbol of hope for those in desperate need, and despair for those who wait, often in vain, a lottery with too few winners, where the odds are stacked against those who need it most. What if we could end the lottery, rewrite the rules, and provide organs for everyone in need, regardless of age, background, or location? That's the promise, the tantalizing possibility of 3D bioprinting. Bioprinting takes our intricate knowledge of genes, the blueprints of life, cells, the building blocks and molecules, the tiny machines that drive it all, and channels it through a printer nozzle, creating complex structures with incredible precision. It's a marriage of engineering precision, the ability to create with incredible accuracy, and biological complexity, the intricate dance of life itself. The result, a hybrid of natural and artificial, a testament to human innovation and our ability to manipulate the very building blocks of life. That could solve medicine's most heartbreaking challenges, offering hope where there was once only despair. The path forward is complex, fraught with technical and ethical hurdles that we must navigate carefully, but the momentum is undeniable. The progress is accelerating. Researchers worldwide are pushing boundaries, refining techniques, sharing knowledge, and getting closer to the ultimate goal of creating functional, transplantable organs. They're not just printing objects, lifeless forms of plastic or metal. They're printing hope, a chance at a longer, healthier life for millions. The story of 3D printed organs is a testament to human ingenuity, our boundless curiosity, and our relentless quest to overcome our own limits, to push the boundaries of what's possible. And this story is just beginning, the dawn of a new era in medicine, where the impossible becomes possible. Imagine creating living structures, layer by layer. But how do you print something alive? It's a question that pushes the boundaries of science and engineering. You can't just use ordinary materials. You need more than plastic or metal. You need bioink, a substance that can nurture and support living cells. Bioink is a life-supporting gel, a carefully designed environment for cells to thrive. It's a carefully crafted mix of nutrients, proteins, and biological materials, each playing a vital role in cell survival and growth. This special concoction mimics the body's natural environment, providing cells with the signals and support they need. It acts as both scaffold and home, providing structural support while fostering a nurturing environment. It's like a cozy apartment complex, holding living cells together while letting them breathe, communicate, and grow. The challenge is to engineer a material that's strong enough to hold shape during the printing process, ensuring the structure doesn't collapse. Yet, it must be soft enough for cells to thrive, allowing them to move, multiply, and differentiate as needed. To achieve this delicate balance, scientists often use natural polymers like collagen or alginate, materials that are biocompatible and biodegradable, ensuring they won't harm the cells and will eventually disappear. Over time, the scaffold dissolves, its job complete, leaving only new living tissue, a testament to the power of bioprinting. Each tissue type needs its own unique bioink recipe, a customized blend to meet specific requirements. For example, bone requires stiffness to provide structural support, while skin needs flexibility to stretch and move with the body. Researchers are constantly tweaking formulas, experimenting with different combinations to optimize cell growth and tissue formation. They're adding growth factors to guide cell behavior, telling them what to become and how to organize. They're like master chefs, meticulously crafting each ingredient, creating recipes not for food but for functioning human tissue, a revolutionary approach to regenerative medicine. The quality of this bioink is the foundation of the entire process, the key to successful bioprinting. Without the right sauce, the masterpiece can't be made. It's the secret ingredient to building the future of medicine. If bioink is the scaffold, stem cells are the builders. Not just any cells, induced pluripotent stem cells or iPSCs, which can become any cell type in the body. Thanks to Nobel Prize-winning research, we can reprogram adult cells into iPSCs, creating a limitless supply from a patient's own body. This solves the problem of immune rejection. Printed organs made from your own cells won't be attacked by your immune system. Scientists then guide these stem cells to become the specialized cells needed for each organ, heart muscle, liver cells, and more. It's like training a team of workers for specific jobs on a construction site. This delicate process requires deep knowledge of how cells develop and communicate. The stem cells are mixed into the bioink just before printing. They're the living component that transforms a gel into functioning tissue. These tiny builders are the true heroes of bioprinting. With bioink and stem cells ready, printing begins. It starts with a digital blueprint, often from a patient's own medical scans, ensuring a perfect fit. The bioprinter lays down the cell-laden gel layer by layer, following the blueprint's intricate instructions. Multiple printer heads can deposit different cell types, recreating the organ's complex architecture. For a kidney, this means building nephrons and blood vessel channels, a huge challenge. Some printers use a second sacrificial ink to create hollow blood vessels which are washed away after printing. Once printed, the fragile structure is moved to a bioreactor, a high-tech incubator that supplies nutrients and simulates body conditions. In the bioreactor, cells multiply and organize, transforming the scaffold into living tissue. Over weeks or months, the printed organ matures, becoming ready for transplantation. This is where the magic truly happens. The journey from concept to reality is marked by quiet but monumental victories. Dr. Anthony Atala's team at Wake Forest grew lab bladders and transplanted them into patients, proving the principle works. In 2019, Professor Tal Dvir's team in Israel 3D printed the world's first vascularized heart. Small, but a complete structure made from human cells. Scientists have also printed skin grafts, cartilage, and corneas, already changing lives. 3D printed bone has even been used to reconstruct faces after accidents. Each success refines the techniques needed for more complex organs. Even space is a lab. In 2019, cosmonauts bioprinted tissue on the International Space Station, where microgravity allows for more delicate structures. Printing in space could unlock new possibilities for organ complexity. These advances are building the foundation for the next revolution in medicine. Every printed tissue brings us closer to printing whole organs. The future is being built one layer at a time. Despite the remarkable progress we've witnessed in bioprinting, and the exciting breakthroughs that have captured our attention, printing a fully functional human organ, one that can seamlessly integrate into the human body and perform its vital functions, is still a formidable mountain to climb. It represents one of the grand challenges of modern medicine. The single biggest challenge, the Everest of this bioprinting mountain, is vascularization. The ability to create the intricate network of tiny blood vessels, the microscopic capillaries, that are absolutely essential to keep thick, complex organs alive and functioning. Simple tissues, like cartilage for example, don't need a direct blood supply, as they receive nutrients through diffusion, but complex organs like kidneys and livers, with their dense cellular structure and high metabolic demands, absolutely do. Printing these incredibly complex networks, where capillaries are often thinner than a human hair, demands a level of precision and control that is currently beyond the capabilities of most current 3D bioprinters. The use of sacrificial inks, which create temporary channels for blood vessels, does offer some help, but as of now, no one has yet succeeded in printing a fully functional large-scale vascular system that is ready for transplant into a human being. Scale and speed are also significant hurdles that must be overcome. The reality is that printing a full-sized kidney, with all its intricate structures, could potentially take weeks or even months, and keeping the delicate cells alive and thriving for that extended period of time is an incredibly tough challenge. Currently, the entire bioprinting process is both slow and incredibly expensive, making it not yet a practical solution for the tens of thousands of patients currently waiting for life-saving organ transplants. Undeterred, scientists and engineers around the world are racing to develop new generations of faster, more precise printers, as well as more advanced bioreactors to nurture and mature the printed organs. And then of course comes the ultimate challenge of function, because a printed organ must not only look right, with all the correct anatomical structures, but it must also work right, performing all the complex functions of a natural organ. The individual cells within the printed organ must be able to self-organize into functional units and respond appropriately to the body's complex signals and regulatory mechanisms. Ensuring that a printed organ truly functions as intended and can seamlessly integrate into the body is a monumental task that requires extensive research and testing. Rigorous testing, using a combination of in vitro and in vivo models, is absolutely essential before these bioprinted organs can ever be safely used in human patients. The summit is in sight, we can see it, but the climb, with all its challenges and complexities, definitely continues. The global organ shortage is a silent crisis millions wait, and every day people die for lack of a donor. Patients endure years on dialysis or face the dangers of the black market. The current system relies on tragedy. A life saved often means a life lost. As populations age, the need for organs grows, but supply can't keep up. 3D bioprinting offers a future where organs are manufactured, not harvested. No more agonizing waits. An organ could be printed on demand, perfectly matched to the patient. This would transform transplantation from a desperate lottery into a predictable, life-saving cure. The stakes couldn't be higher. This field is built by brilliant minds at the crossroads of biology and engineering and computer science. Dr. Anthony Atala and Professor Tal Devire proved the impossible is within reach. Dr. Jennifer Lewis at Harvard developed revolutionary bioinks and methods for printing vascular networks. Companies like Organovo are bridging research and real-world applications, starting with drug testing and aiming for transplantable tissues. These pioneers are part of a global effort, sharing data and solving problems together. Their vision, a future free from organ waiting lists. They're mapping a new world of medicine and building the ships to get us there. Their dedication is turning science fiction into science fact. The future of medicine is being written in their labs. We're living at the dawn of a new era in medicine. Printing replacement organs is no longer a dream, it's becoming reality. The progress is breathtaking, but challenges remain. Imagine printing pancreatic tissue to cure diabetes or neural tissue to repair spinal injuries. This technology could revolutionize drug testing and even how we age. With such power come ethical questions. Who gets access? How do we use it fairly? The best way forward is to stay informed and engaged in the conversation. The story of 3D bioprinting is a testament to human curiosity and ingenuity. Follow ScienceDeeps for more mind-blowing science facts.